Okay, so next we're going to take a look at another L'Hopital's rule applied to exponentials, right? So in particular, we're going to look for limits that are of this form, either 0 to 0, positive infinity to 0, or 1 to infinity. All right. So we're going to try to evaluate these limits using our properties of logarithms, and then the L'Hopital's rule as we defined earlier, right? And again, L'Hopital's rule are indeterminate forms that are like this, right? Now we developed other techniques that didn't start off like this, but we were able to manipulate in order to make it like this. Okay, so we're going to do that here, right? So we're going to start off with our first example here. So we're going to have the limit as x goes to 0 on the right of x sine of x. Okay, so as x goes to 0, this value for x goes to 0, sine goes to 0, so we have 0 over 0. All right, now the approach I'm going to take is, let's say that this limit exists, right? This limit is some finite value, or positive infinity or negative infinity, but it does exist. So I'll set this value equal to L. Then I'll use my properties of logarithms by taking the log of both sides. Ln of x sine of x equals to ln of L. All right, and L is going to be the limit of this, the value of this limit, excuse me. Okay, so from here we just start applying properties of my logarithms. Bring the exponent down here as a coefficient. And now, if we look at the limit, we have, as x goes to 0, we got 0 times infinity. But I already seen in the previous video that I can work with this by just manipulating this algebraically. So I'm going to write this as ln of x. Reciprocal property tells me that 1 over sine x, but that's just the cosecant of x. All right, and that is ln of L. And now as x goes to 0, this is going to 0. Excuse me. 1 over sine of x, so sine of x is going to 0, but 1 over 0 is going to infinity, and natural log is going to infinity as x goes to 0, right? So we have a limit of this type. So now we can apply L'Hopital's rule. So applying L'Hopital's rule, we get 1 over x. Derivative of cosecant is negative cosecant x, cotangent x. All right. And now, again, equals to ln of L. And then here, applying the reciprocal property, we got the limit as x goes to 0. Here, negative sine x tangent x over x equals the ln of L. All right, and again, still 0 over 0, right? As x goes to 0, x is tending to 0. Sine of x and tangent of x both are tending to 0. Okay, so one more time, limit as x goes to 0, right? This is now 0 over 0. So this becomes negative cosine x tangent x minus sine x secant squared x all over 1. All right, and then from here equals ln of L. Plugging that in, so this goes to 0, that goes to 0, so plugging in 0 is equal to ln of L, which means that, again, inverse properties of the natural log, e to the 0 is equal to L, or L is equal to 1, which means that, going back to my original limit, that we started with, the limit as x approaches 0, x sine of x is in fact equal to 1. All right, so that's how you approach these limits here. All right. Okay. All right. So now again, we'll take a look at how about the limit as x goes to infinity of x to the 1x. All right. So now this one here is of the type as x goes to infinity, x is tending towards positive infinity, but 1 over x is tending to 0, right? So we got something of the form infinity to 0. And I'm going to start it off the same, right? I set it equal to L, right? Take the natural log of both sides. X, 1 over x equals to ln of L. Here, applying properties of the logarithm. So we got limit as x goes to infinity, 1 over x ln x is equal to ln of L. All right. Okay, so here it is. So both of these here, I'm going to rewrite it here. As ln of x over x. Right, and again, as x goes to infinity, the numerator is going to infinity and the denominator is going to infinity. So now we're of the form infinity over infinity. So we take the derivative, so the limit as x goes to infinity, we get 1 over x, right? And then over 1, right, equals to ln of L. All right. Which means here that, all right, that goes down 1 over x as x goes to infinity. This whole quantity is getting smaller and smaller, so it's approaching 0, right? Properties of exponential and the logarithm, e to the 0 is L, or in other words, 1 is equal to L, or the limit as x goes to infinity of x to the 1 over x, that's equal to 1. Okay. All right. Now, here, our last example here, the limit as x goes to 0 of 1 minus x, 1 over x. All right, so this one as x tends to 0, we get, this is of the form 1 over infinity. Or 1 raised to infinity, excuse me. Okay, so again, this is set it equal to some value L, and then take the natural log of both sides. So we get limit as x tends to 0, 1 over x, ln of 1 minus x equals to ln of L. Okay, and again here, this is tending to infinity, and that's tending to 0. So here we have infinity times 0. Rearranging this, we have the limit as x goes to 0 of ln 1 minus x over x. Okay. Okay, so now we see here as x tends to 0, the top is going to 0 and the bottom is going to 0. So we are of the 0 over 0 indeterminate form. All right, and then taking the derivative here, right? Derivative of the denominator is 1. Derivative of the top, we're left with 1 over 1 minus x here. And then the chain rule says we have times -1. Okay. All right, so as x goes to 0, okay. Okay, equals to ln of L. Then I can plug in 0 here, and we get -1 is equal to ln of L. Or in other words, e to the negative 1 is equal to L, or 1 minus x, 1 over x is equal to 1 over e. All right. So an interesting result here, right? Get this equal to the exponential e.